Now I will present a series of lectures about networks as a base for distributed computing. Well, first of all, we will examine what it really means distributed systems. There are a lot of definitions from Couloris, Tannenbaum, Lamport. According to Couloris, a distributed system is one in which components located at network communicate and coordinate their actions only by passing messages. So, Couloris talks about message passing has the main, not just the main, but the only way for process to coordinate actions and to communicate. Once there are no such thing like shared memory. According to Tannenbaum, a collection of independent computers that appears to its users as a single coherent system is a definition for distributed systems. So here we have a systemic view. A distributed system behaves as just one system in now. The users do not concern about the parts of the system. So there is just one large system composed by a large of parts located in different nodes in parts of infrastructure in one site, other parts in another site. So there is a systemic view. And Lamport emphasizes the role of faults. A distributed system is one that prevents you from working because of a failure of a machine that you have never heard of. What that really means? A distributed system is composed by many hardware and software components. If some of these components fail, the system may fail. We can configure the system in sense of there is something of like fault tolerance. So if a component fail, other components may tolerate the fail. But for doing this, we have to be aware that the first nature of distributed systems, because distributed systems are systems more complex than centralized systems, and are systems that the function depends on the function of a large number of components that are located in different sites. These definitions emphasizes things like message passing, absence of a shared memory, of a global clock, of a centralized software structure that presents a global behavior for the system. Fault independence, concurrent execution processes are located in different sites and different nodes and may execute concurrently. Impossibility of keeping a constant picture of the global state. We will see that the global state is more like a panoramic photo in the sense of you take photos of parts of the system and compose a panoramic view that represents our system, but in fact, it's not an instant picture because you have to take parts of the global state in some different moments. You cannot take an instant picture of the global state as well, because we have no global clock, we have no shared memory, we have no shared infrastructures that can be synchronized with no lag now. There is such a lag, even when a little lag. Distributed systems are in all parts. I see distributed systems everywhere. In avionics systems, we may perceive that there are a lot of subsystems of sensors, actuators, boarding computers that interact with each other. We have systems to control refrigeration, to control entertainment system, to control navigation, and the systems may interact with each other, forming a large distributed system, all in a single plan. And we have things like cloud computing, where we can use internet to get on-demand system, on-demand services based on applications, based on the storage, based on computational services. So if you use the OneDrive or Dropbox, you are using a storage service located in a cloud computing, and you may have replicas for each file that you put into services. And it's an example of a distributed system. Other examples are from financial markets. We have brokers, and these brokers may interact to trade shares each other, passing orders to sell or buy shares in such a way that they compound a large distributed system. And these systems in general are heterogeneous. We have different operating systems, different platforms, different vendors of software and hardware, and we may use the open patterns, open architectures to make all these different parts to communicate with each other. It's a very common scenario. So the arena for distributed systems are in general up to network. Many people may think, okay, I use distributed systems in network, in computer networks, in the internet, in the intranet. So distributed systems is an extension of a computer network. Not at all. Distributed systems are concerned of the application layer of a computer network. So in general, you compound the application services that you run over a platform. What is a platform? A platform is a composition of computer router and network and its operating system and library services. In sense, you may develop a distributed system using, for instance, sockets. If you use sockets, you are interacting to operating system, to libraries for use TCP sockets or UDP sockets. You may have a lot of effort to make this applications to run, and a lot of details to concern. But in general, we have middleware, and middleware is an intermediate layer of software that facilitates the use of distributed computing and abstract details of the platform. And so if I use a middleware like RMI, for instance, I may use distributed objects in Java and have no concerns about sockets, about where is located the distributed object, for instance, and I may improve my productivity to develop these applications and to deploy services, to deploy distributed services to the network. So we will abstract out the infrastructure and focus on process. Processes are programs running. So here we have P1, P2, and P3, three processes executed by nodes that are usually distinct. In this figure, P2 and P3 aren't the same node, but they usually may be located in different nodes. And communication channels. Communication channels, so we have for three processes, a communication channel P1 to P2 and P2 to P1. It's a bidirectional communication channel. P2 to P3, P3 to P2, and P1 to P3 and P3 to P1, including all hardware and software infrastructure, operating systems, computer networks, libraries, all the stuff that may put in contact a process to another process. So if a process needs to send an information to other process, it will use a communication channel related to that process. And a program based on these abstractions of process and communication channels, we abstract out the details of platforms, of the computer networks, of other stuff, in the sense that we may focus on the problem of coordinating actions between processes. That is really a large effort for distributed systems. What's the better for distributed systems? Program coordinating actors between concurrent processes is not a trivial task. If I must to coordinate actions between processes, I have to be concerned that may I use the synchronization mechanisms that are different from the synchronization mechanism that I will use in centralized systems. If I have a lot of processes running in a same node, I may use the semaphores, I may use the barriers, but if these processes are running in different nodes, I have to use the other primitives, or to adapt these primitives to a distributed scenario. Because there's no global information, no shared memory, no single clock, no a single point of synchronization that may use a global oracle that will see the system has world in an instinctive picture. Yeah? So the problem is based on the first nature of distributed system, that is the use of message passes. In a increasing degree of difficulty, is much simpler to program single programs. If I have to coordinate actions from concurrent process running in a same node, I may use a shared memory, I may use the semaphores. There is a little bit more degree of difficulty. But if I must to program a concurrent process running in distinct and different nodes, I have a more interesting and a more challenging scenario. And how to solve that? How can I solve this problem to program in such a hard scenario? I have to abstract the details. I have to focus on the details that are relevant for the problem, for others the problem. So everything is based on providing guarantees in the infrastructure to have adequate premise for the coordination of these actions. So I will see the properties of the system, and based on that, focus on the premise that the properties provide, and put that in a model that encapsulates the premise. So the focus on building applications is on models. So everything that's not relevant is abstracted. In general, the use of middleware implementations take care of the things that should be abstract. Or if there is no shared global memory and I use message passing, time information is important. If a process P1 sends a message to process P2, maybe the timestamp of when that message was sent may be used to coordinate some actions. Yeah. But there's more challenging things to concern, because P1 is on A site, P2 is on B site, and A site and B site use different clocks, because the two sites are different nodes, and there is no such way to perfectly synchronize clocks. So I must have strong confidence in time limits based on the premises of the infrastructure, because in some scenarios, I may synchronize the clocks, not perfectly, but I may. And I may use that information to provide some hints of how to coordinate actions. For instance, if P1 knows that it sends a message to P2, P2 processes that message and responds that, and P1 is aware of time limits of communication channels between P1 and P2, and the process time of execution the message in P2, P1 may know a hard limit that it will expect an answer from P2. If there is no such answer, it may assume that there is a fail and P2 is not responding. So it may exclude P2 from the process of computing that request, and allocate the resources and delegate the role to execute that action to another process like P3 or the other process We encapsulate that in the sense of interaction models that really provides the way the process interact with each other in terms of time. The more strong premises are the synchronous premises or timeless premises. When I say we use a synchronous model, I say that I use a network with a maximum deterministic latence. I know the maximum latence between the nodes. I know the nodes have well-behaved clocks and execution limits, so the clocks does not deviate so much each other. in the sense I may periodically synchronize the clocks, and I have execution limits. So if P2 executes an action, I may say exactly when P2 with absolute certainty should be already executed that action. So I needed to use strong premises in a strong infrastructure based on deterministic networks like Ring, GPS synchronizations, real-time operation systems that are strong and useful features. Yeah? In many cases, I may use the other things that are strong enough to provide a behavior that most of the time is very close from asynchronous behavior to asynchronous behavior, like oversized networks that the resources are much more than the resources needed. Yeah, using quality of services, using local network timing protocol to provide synchronization, process running on dedicated operating systems, so a process may not compete with other processes in the same node, and I have a certainty in the limits of the execution, and such premises are more feasible. What does this allow? Periodically synchronize the clocks, maximum response time, ordering time transactions executing on different nodes. I may have a distributed transaction that is coordinated between different nodes, and I may use timestamps to know if I receive a node requisition or a new acquisition, how I should process that, for instance. In the other way, I may talk about a synchronous model where I have no network guarantees, no execution guarantees, like internet. Internet is clearly asynchronous. What does this impose? This does not impose anything. In this way, applications with scenario can only estimate a maximum response time and cannot order all transactions that occur on different nodes based on timestamp. I may have only a suspicion if P2 is not responding, because I may not say that there is a failure or that the network is with a great delay, or even the process is with a great delay. I may not say that these things. And we have the middle way. We may talk about partitionally synchronous. There is a category of systems that assume characteristics that some parts of the components have a timely behavior, have premises of well-known timely limits, and the other parts are not. Or in some instant of the time, the system has world behaviors, has a timely system. So we may speak about partial synchrony, timed asynchronous, that are systems that we assume things like a global stabilization time, where the systems has world behaviors, has a well-behaved system, and we may assume some time limits and may use that time limits to make assumptions about the coordination of actions and about failure suspicious, for instance. Or we may say about systems like timely computing base, where I have a network where I may establish using quality of services channels that provide a spanning tree between the process that is a control overlay network where I may have a timely behavior. I may use that control overlay network to provide control methods that we use to coordinate actions based on time between process. And the majority of data is not using that overlay network. The majority of data circulates using asynchronous communication channels where there is no assumption about time. So I may coordinate some actions using the control network. At the same time, I does not have to provide stronger resources to have as I should to provide in a world synchronous network. And the same way, we may speak about hybrid active and a model and the SPA model. SPA model, for instance, is based on partitions that are clearly synchronous islands, but these partitions show this communicate each other through communications communication channels that are asynchronous. It's a very common scenario where you may have a set of nodes located in one site and a set of other nodes located in another site. Inside a site, we may provide strong resources, we may provide a dedicated switch, we may provide dedicated infrastructure, but that site communicates with another site through internet where I can't provide all this stuff. So process 1 may monitor process 2 and process 3, for instance, because they are located in the same site, and to provide information to process 5 that process 3 is not responding. Process 5 may not monitor directly process 3 because once the communication channel between process 5 and process 3 is an asynchronous communication channel, I have no timing limits that I may use. I may have only a barely suspicious. The use of sequence partitions can allow you have reliable information with the partition. So the partition that we have process 1, 2, and 3, we may have reliable information from 1 about 2 or 3, and use this to provide information to process 5, 4, and 6 for computing as well. So in this first video, we talk about synchronous, asynchronous, and partially synchronous models. We talk about a view of distributed systems, the role of distributed systems, and the next parts of this lecture will extend this explanation through failure detections, through failure models, through building blocks of distributed computing. Thank you for all the audience.